About 90% of U.S. electric power is generated via a thermal process in which heat is converted into mechanical work. The source of the heat can be from the combustion of a fossil fuel, from a geothermal source, the result of a nuclear reaction, or the concentration of focused sunlight. The heat source is then used to turn a turbine, either using a liquid working fluid, such as a steam, or a gas working fluid, or sometimes a combination of both a liquid and a gas with two separate turbines. Therefore, at a basic level, electric generators are driven primarily by heat engines, usually steam engines, gas turbines, or internal combustion engines. A heat engine will extract heat, HQ, from a high temperature source, such as a boiler. It will convert part of the heat into work, usually in the form of a rotating shaft, and then it will reject QC, the remaining heat, into a low temperature sink, such as the atmosphere or a body of water. Now, a lot of times we have confusion between the terms or the concepts of heat and temperature. Heat is a total energy of molecular motion in a substance, while temperature is a measure of the average energy of molecular motion in a substance. So heat energy depends on the speed of the particles, the number of particles, including the size or their mass, and the types of particles in an object. Temperature does not depend on the size or type of object. For example, the temperature of a small cup of water might be the same as the temperature as a large tub of water, but the tub of water has more heat because it has more water and thus more total thermal energy stored in it. So you could extend this even further. What has more heat energy, a small Dixie cup of hot water or a iceberg? And well, you can't say for certain, but there's a good chance that the iceberg has more heat energy depending on the temperature differences and the size difference, even though its temperature is much colder. Right? So the concept that I want to get across is that it's heat that will increase or decrease the temperature. If we add heat, the temperature will become higher. If we remove heat, the temperature will become lower. Higher temperatures mean that the molecules are moving, vibrating, and rotating with more energy. If we take two objects which have the same temperature and bring them into contact, there will be no overall energy transfer between them because the average energies of the particles in each of the objects are the same. If the temperature of one object is higher than that of the other object, there will be a transfer of energy from the hotter to the colder object until both objects reach the same temperature, a state we call thermal equilibrium. So what I'm really trying to get across is temperature is not energy, but a measure of it, average measure of it, and heat is energy. Right? So there was a scientist for many years who studied these heat engines. His name was Carnot, and he developed formulas for us to analyze these kind of heat engines that we're showing here. And we have the thermal efficiency of a heat engine is defined as the ratio of work done to the input energy provided by the high temperature reservoir. So my thermal efficiency, and remember our symbol that we've been using in this course for efficiency it's like this cursive N, eta. In this case it's going to be thermal, so we're going to give it a subscript T. And we said that it's the ratio of work done to the input energy provided by the high temperature reservoir. So the thermal efficiency is just how much work did I get out divided by the thermal energy Q of the high temperature reservoir. And due to the law of conservation, if I've got my heat source, remember I've got the heat source and there's QH flowing out of it. This is the engine, and the engine does some work in the form of the rotational shaft, and then it ejects some sort of waste heat energy, QC, this being the cold surface. such as the atmosphere or such thing. Law of conservation of energy, I know that W plus Q sub C has to equal QH. So I can rearrange that and I could solve that for work. I would say that the total work done is just equal to the difference in energy between the Q hot and the Q cold. So I can then substitute this equation here into thermal efficiency. And so thermal efficiency is just going to be Q hot minus Q cold over Q hot. That's equal to 1 minus QC over Q hot. So in this equation, the maximum efficiency of the heat engine has to be a function of the temperatures of the hot and cold reservoirs. The QC and QH have to be a function of temperature. And so if we want to fully describe this relationship, we have to understand a second thermodynamics concept that we call entropy. So we're going to kind of put the brakes on this guy here for right now, and we're going to stop and we're going to look at a concept called entropy. In the study of thermodynamics, the concept of entropy is kind of a measurement of molecular disorder. The classic description of entropy is stated as nature tends from order to disorder in isolated systems, which I've expanded upon by these following cartoons that I stole from the Hyperphysics website. What they're showing is that I've got a very ordered system, and over time the system will become more disordered. Sometimes I've heard this described as nature abhors a vacuum as another way. So spontaneously in nature, systems do not rearrange themselves such as this over time. For example, if I were to put a droplet of dye into a body of water, we know that that droplet of dye is going to expand out and mix with the molecules of the water, and eventually the droplet will have spread evenly throughout the water. And that's kind of what this is showing. We know that it doesn't go the other way. That water never spontaneously, that droplet of dye never spontaneously extracts itself from the water and concentrates in one given area. Another kind of funny example is if you were tossing bricks off the back of a truck, you know that naturally you're probably going to end up with an unordered pile of bricks, not this neatly stacked pile of bricks. At one end of the entropy scale, we have order. For example, a purely crystalline substance at absolute zero temperature with every atom locked into a predictable place. That atom is exactly there because there's no thermal energy. That atom is exactly there because of no thermal energy. An atom, a crystal such as this would have no entropy. A solid at room temperature, however, these crystalline atoms, they'd have some vibrational energy. So would it be so perfectly ordered? No, because each of these little guys would be vibrating around, and its actual position would therefore be a statistical quantity, right? So it's got increased entropy as compared to the crystalline structure at 0 degrees Kelvin. When we burn a fuel source, such as coal, what we're doing is we're increasing the entropy of the fuel. Unlike energy, entropy is not conserved in a process. In fact, for every real process that occurs, disorder will always increase, and the total entropy of the universe is going to increase. So electricity generation can really be thought of as increasing the total entropy of an isolated system, that system being the fuel source in the power plant. So if we want to put this in terms of temperature and heat, if we have a amount of heat Q, if we remove that heat from a large thermal reservoir at temperature T measured in Kelvin, such that the temperature of the reservoir doesn't change as a result of the heat loss, the loss of entropy from the reservoir is equal to delta S, right? So I've got some large thermal sink such that taking energy, or thermal mass, excuse me, such that taking heat out of it doesn't actually influence its temperature. So it's kind of an infinitely large approximation. It's at some temperature T. I remove a certain amount of heat energy such that T doesn't increase. Well, because I've removed heat energy from it, I have decreased the entropy of the system. I represent that decrease as delta S, a change in entropy. So S is entropy, right? So let's take this equation and apply it to the equation we had produced previously, where we had, well, I'll just rewrite it here. It's the thermal energy is equal to 1 minus QC over QH, right? The heat energy of the cold source and the heat energy of the hot source. So now let's just write, there's two delta S's, because remember we're removing heat energy from the hot source and we're ejecting it into a cold source. So we've got delta S for the hot source is just equal to QH over TH. And then when heat's added to the low temperature sink, its entropy has to increase. So we've got the entropy increase of the cold source is just equal to QC over TC. So as we stated earlier, for every real process, entropy must increase or at best break even, which means when considering the entire process, the entropy gained by the cold sink must be equal to or larger than the entropy loss of the high temperature reservoir. So what I'm saying there is that the entropy gain of the cold sink, delta SC, has to be larger than or equal to the entropy gain of, or the entropy lost by the high temperature source, delta SH. So I can just take these two and plug them in. That gives me QC over TC in a heat engine must be larger or equal to than QH over TH. And I could do some that's a C, that's a terrible looking C. But I could do some cross multiplication here, and I could say QC times TH has got to be greater than or equal to QH times TC, and then I could do some division, and I would end up with QC over QH. So the heat energy of the cold source divided by the heat energy of the hot source must be greater than or equal to the temperature of the cold source divided by the temperature of the hot source, TC over TH. So I've got this definition here. I said the N sub T has to be 1 minus QC over QH, and then I can plug this in here, and I end up with N of a thermal system must be 1 minus TC over TH must be less than, TC over TH is less than, so this becomes less than or equal to 1 minus TC over TH. So this gives us really a maximum theoretical possible efficiency of a thermal engine. We see that the thermal engine's max efficiency is, and this will give us a decimal, so just multiply this by 100, right? If the temperature difference is, if there's no temperature difference, the efficiency is going to be 0, 1 minus 1. The larger the temperature difference between the two is what drives this the thermal efficiency. So a lot of times this is written as Nmax. Nmax is equal to 1 minus Tc over Th. So really, the bigger the thermal differential between the cold source and the hot source, the more efficient that we can make these systems. Since neither infinitely high temperature nor absolute zero temperature are actually possible, no real heat engine can convert thermal energy into mechanical energy with 100% efficiency. There's always going to be waste heat rejected into the internal environment. So this kind of tells us, if we know the difference between the two, what the maximum theoretical efficiency is, and we know that by this law, by Carnot's law of thermal efficiency, that we cannot have a heat engine that is any more than 100% efficiency. So when you're on cable news or cable access and somebody's selling you a perpetual motion machine, you say, Carnot's law of thermal efficiency proves that that's an impossibility.